Okay, so today we're going to talk about section 7.2. It's about hypothesis testing. When you guys were here last time, we introduced it a little bit, and we talked about how it works and what kind of errors you can make, and today we're going to work through the details. That is our plan. I think that probably the best thing to do with this would be to just jump in and look at a few examples. So let me give you a quick overview, and then we'll just do a bunch of examples. We'll try a few using technology, and then we'll see if you guys have any questions, and that might be it for today. So hypothesis testing. Here's how it goes. You suspect you would like to test some parameter of a population. And so we want to test maybe that the mean is what they say it is. But we could test we're going to test the mean and the proportion. But you could also test the variance or the standard deviation or lots of other things. We're just going to get a feel for hypothesis testing by testing the mean. Okay, and then there's going to be two situations. There's going to be a situation where we know the standard deviation of the population and one where we don't. So that's going to be 7.2 and 7.3. If we know, well, it's likely that we do know the standard deviation of the population and the mean of the population, because what we're really saying is there's an advertised number, right? Somebody is claiming that they've got this population and they know what the average is and they know what the spread is. And we suspect that maybe it's wrong, or we just want to test to see if it hasn't changed. And so what we do is we go out and we take a sample, and then we say, okay, what's going on with this sample? Is the sample what we would expect to get if the mean and the standard deviation are the way they were stated? Or is this sample so rare that it would be so unlikely to happen by chance that we suspect that maybe the average of the population is different from what they said? So, a specific example. Here's one in the book. Okay, it says oops, I got to change my thing over so I can zoom it. What's going on here? There. Okay, so this is page 366. So if it's not coming through real good and you guys want to look at it on your own screen, you can open up the book. It says, in auto racing, a pit stop is where a vehicle stops for tires and fuel and repairs and other mechanical adjustments. Okay, so the efficiency of a pit crew that makes the adjustments can affect the outcome of the race. A pit crew claims that the mean pit stop time for tires and fuel is less than 13 seconds. So maybe they're vying to be move up in the world and be a pit crew for a celebrity or something. A random sample then, and so you say, well, I don't know, maybe it's a little more, maybe it's a little less. Okay, and you would have to know about pit stop times. Are pit stop times normally distributed? Kind of seems like they would be. You know, there would be an average, and then some will be a little more and some will be a little less. Okay. So what you do is you wonder if the 13 seconds is a true number or not. So what you do is you take a sample. And in this particular problem, they sampled 32 pit stop times. Okay. And they ended up with a sample mean of 12.9 seconds. Just a little bit less than the 13 seconds that was advertised. It says, assume that the population standard deviation is 0.19 seconds. Okay, 0.19. That's not very long, a little less than 0.2 seconds. And our sample mean came out to be 12.9, just 0.1 second smaller than what was advertised. The question is there enough evidence to support the claim? The claim would be, what did they say? That it is less than 13. Okay? So what you do first is you try to get your head wrapped around this problem and then translate it into some symbols, right? You're going to make a hypothesis and a null hypothesis. You're going to then do the calculation and figure out what's happening. But essentially what they're doing is this. the claim is that it's going to be less than 13 seconds. So 13 seconds is the big cutoff. Would a sample of size 32 with a mean of 12.9 be really unusual if the mean of the population was 13 seconds with a standard deviation of 0.2? That's the question. And I mean, just thinking about it doesn't seem like that would be that rare. But let's draw a picture of it, okay? Let's say pit stop times are normally distributed, okay? And even, it turns out, if they're not normally distributed, if we sample more than 30, then the distribution of all the sample means will end up normally distributed. Okay, so here's our mean. The mean was 13 seconds. The standard deviation, right? The standard deviation was 0.19 seconds. And so check out all the pit stop times. 68% of them are going to fall in this range, right? From -1 to 1 standard deviation. So from 13.2, from 12.8 to 13.2, basically. Then 95% of them are going to fall in this range. Okay, then 99% are going to fall within 3 standard deviations. So 99% are in here. And of course, these numbers are rounded off, and you can get the exact numbers by using your calculator. Okay, so it's basically what it comes down to then, see if I get it to focus, is how weird, right? How weird would 12.9 be? So 12.9. So this is, let me get my calculator so we can do some exact numbers. Right? If you have an average of 13 and you take away 0.19, then you're down at 12.81. 12.81, and I take away another 0.19, right? Then I'm down at 12.62, and then I take away another 0.19, and I'm down at 12.43. That's a 3. And then if I go the other way, and I take 13 and I add 0.19, then I'm up 1 standard deviation at 13.19. If I add another one, I'm at 13.38, right? And if I add another one, I'm at 13.57. So I would argue that a pit stop time of longer than 13.57 would be really rare. That's way over here. It only happens less than 1% of the time. And a pit stop time of less than 12.43 would be really rare, again, happening less than 1% of the time. So we want to know, well, how weird, right? How weird is an average, a sample mean of 12.9 seconds? All right, how weird is that? You'd say, well, I don't know, 12.9 falls right in here somewhere, right about there. And I would say that's sort of right in the middle of what I would expect to happen. So 12.9 isn't that, isn't that weird? I mean, and that's it. So you'd say, well, I took a sample, but look, this was one value. One value of 12.9 is not that weird. But now the question is, what about if I took a sample of size 32? So if you took a sample of size 32, you would get some values over here and some over here and some in the middle. The question is, how weird would a sample of size 32 be? If this was just a sample of size 1, then one value of 12.9 isn't that weird. The question is, well, okay, what about a bigger sample? So we look at the distribution of the sample means. In other words, we look at the distribution of all samples of size 32. Now, because the sample size is 32, the distribution is going to turn out normally distributed. It's going to be centered at the same place that the population mean was, but its spread is going to be the standard deviation of the population divided by the square root of the sample size. So it's going to be less spread out. In other words, it's much more unlikely that a sample of size 32 is way over here than it is if just a single value is way over here. So how unlikely? I don't know, we got to do the numbers. Okay, so here's the spread. Okay, and the spread would be the standard deviation of the population. In section 7.2, we're going to know this number. In section 7.3, we're going to approximate this number with the sample standard deviation, which is going to introduce a little more error, and we're going to have to use the student t-curve instead. Okay, but in this problem, let me see if I can look it up. What did it say? It said it had a standard deviation, oh, I wrote it up here, of 0.19. I'm going to divide by the square root of the sample size, and I'm going to get a spread of 0.19 divided by square root 32, which is 0.03335 is what it is. So I'm going to round it to 0.34. Okay, so here's the mean. I didn't leave myself a lot of room to write. I'll write this up here. The mean is the mean. And then I'm going to write down here that the mean was 13. So if I go over one standard deviation, now I only go over to 13.034. In other words, samples of size 32 are a lot less spread out. If I go back the other way, I've got 13 minus 0.034. So at 12.966. And if I keep going, two standard deviations minus 0.034, I'm at 12.932. And if I subtract another one, I'm at 12.898. And then going this way, two standard deviations, 13.034 plus 0.034 more, 13.068, and three standard deviations plus 0.034 more would be 13.102. So this is the distribution of all the samples of size 32. And so what would we expect? We'd expect samples of size 32 to be spread out around the mean, okay, but only ranging down to 12.966 and up to 13.034, 68% of them. Of course, 99% of them, right, would fall in this range. 99% of all samples of size 32 would fall between 12.898 and 13.102. So about 99% of them. So then the question is, all right, while a single pit stop of 12.9 is not weird, right? Maybe we should have just said the average of size 1 is just the number, right? So maybe we say an X of 12.9 is not that weird. But down here, we're looking at a sample average, or a sample mean of 12.9. So how weird is 12.9? Okay, I don't know. 12.9, this is 13, 12.898, 12 point, it's about here, isn't it? So if you're way down here, look, you're more than 2 standard deviations away from what you expected. more than 2 standard deviations is pretty weird. So how could the sample end up down here? Well, one way is that it could just be bad luck. In fact, if we look up exactly how much area there is over here to the left, we can figure out exactly what the chance is. So what's the chance that I fall in this region? Right? We're going to have to find the area. So to do that, we're going to use the calculator, and we're going to say normal, right, CDF, and we're going to say I want to be to the left. So how about 1E99? Okay, all the way to the left, 12.9. And then the mean was 13, and the standard deviation was our 0.034. So if you want to put it in exactly, instead of rounding it, you can say 0.19, or you can say 0.19 divided by the square root of 32. In other words, just put it in exactly. Okay, pushing return. We've got the area over here, this little bit that's left, right? Our p-value is going to be 0.00145. So we'll say 0015. There's only a 1/10 of 1% chance that I'm over here. Okay, it's not very good. And so then the question is, how could I fall over here? Well, maybe you just picked a sample. Maybe you just got really lucky, or unlucky as the case may be, and you just picked 32 of the fastest pit stops that this team's ever had. Okay, could it happen? Yep, about 0.15% of the time, less than 1% of the time that could happen. So since that's pretty unlikely, the other way that it could be over here is that the mean, right, could actually be smaller. If the mean were smaller, then being over here would not be unusual. So we say, well, I don't know, what's more likely? Is it more likely that I picked this sample of really quick times? In other words, this 0.1% of the time chance? Or is it more likely that the mean is probably not 13 and is actually a little bit faster than that? And we would say, we think that based on this sample, since it's so unlikely to get a sample way over here, we think that the pit stop times are actually a little bit faster than 13. And that would be our conclusion. Okay, so what I didn't do is kind of formally write down the hypotheses. So let me go back and do that. The hypothesis is, the null hypothesis is that it didn't change. In other words, that the mean is less than or equal to 13. The null hypothesis always includes the equal. So it's equal to 13 or less, meaning that the alternative is everything left over, that the mean is greater than 13. And so what do we do here? We say, it looks to me, since the chance was only 0.1%, that probably the mean is less than or equal to 13. Okay, and in this case, we would fail to reject the null hypothesis, right? We would say there's, wait, let me say that correctly. We would say, we would reject, did I write these backwards? I think I did. The null hypothesis is that it's greater than or equal to 13, and that it's less than 13. We would say that the evidence, right? The evidence shows that it's less than or equal to 13, and we would reject the null hypothesis. Okay, so that's kind of how that's kind of how this thing works. You've got a population mean. You're saying, do I think this mean is right or not? You take a sample. If the sample is really unusual, then you say, no, I think the mean is different from what they said. Okay, so that's how it goes. Questions about that?
Nope.
All right, well, let's try a couple more examples and see if we can kind of streamline this without going through quite so many details. I think that after you do a bunch of these, you can kind of get to where you can do them fairly quickly just using your calculator. But I think for the first few, you should probably go through them the way we just did and make sure you draw the picture and think about, where does the sample statistic fall, and look at the pictures. I think that really helps. All right, so here's number 2. Here's another example from the book. Now we're talking about heating equipment. Okay, and it says the mean indoor temperature during winter, well, it's not around here. The mean indoor temperature of US homes at night in the winter is 68.3 degrees. Okay, you think, yeah, anybody here probably think that's incorrect. And even around here, you'd have to air condition to be that cold, even in the wintertime. So you think maybe, what did you claim? Is there enough evidence to support your claim? The claim was, from past studies, standard deviation is this. In the winter, you find it to be 67.2. So you think it's colder. I actually probably would agree with that, having been somewhere colder. If you're worried about Arizona, you'd probably think it's warmer, right? Okay, so here's the deal. They advertise that the average temperature is 68.3. You're thinking that it might be actually a little bit colder than that. So you go and take a sample. If you just take a sample of one house and it turns out to be colder, then you've got a little bit of evidence that says, hey, yeah, maybe it's colder. But because houses, heating temperatures of houses are normally distributed, then you would expect some to be a little warmer, some to be a little colder. So it's not that unusual that you would get one house that's 67.2 if the average is 68.3. Okay, especially if the standard deviation is 3.5 degrees. So really, you would expect, given 3.5 degrees, 3 3s are 9 degrees, you would expect this to be somewhere between, 60 and what's 9 more, 73, 72. So you would expect pretty much every house would be between 60 and 72 degrees. So 67 is not that rare. So instead of just picking one house, you pick a sample of 25 houses. It would certainly be more unusual for all 25 houses, or the average of your sample of 24 houses, to be further away from 68.3. Okay, so then you say, well, let's take a look at what my average came out and ask, how weird is it? In other words, would I expect to get an average this low if in fact the mean is really 68.3? And in this case, we want to test our claim at the 5% level of significance. So we want to say, I want to be 95% sure, right? I only want there to be 5% of the time for samples this weird to have occurred by chance. Okay, so what do you do this time? I'm probably going to draw the picture. Okay, so I'm going to probably draw the picture every time. Notice for these, we either have to have the distribution of all the houses be normally distributed, or we have to have a sample size of greater than or equal to 30. We only got 25 homes. So we're hoping that when we heat houses, that they're normally distributed. it seems pretty reasonable that you would have an average of 68.3 and and then the houses would be distributed sort of mound-shaped, symmetric around there. In this case, with a spread of 3.5 degrees. Okay, so what's weird? What's weird would be one house more than 7 degrees hotter than that, 75 degrees, or one house 7 degrees less, colder than 61. Right? That would be pretty weird because that's more than 2 standard deviations away. But we looked at a sample of size 25. So samples of size 25 are normally distributed, right? So these are sample distribution now. So of size 25. Notice that 25 isn't quite big enough to guarantee that these are normally distributed, but if the population was normally distributed, then the distribution of sample means is also normally distributed. So these things are centered at 68.3. The mean of the distribution of sample means equals the mean, which was 68.3. The spread of the distribution of sample means is the spread of the population divided by the square root of sample size. So in our case, 3.5 divided by the square root of 25, or 3.5 divided by 5. Using my calculator, I have 0.7. So we have a spread of about 3.5 degrees for individual houses, right? But for samples of size 25, they're only spread out like 0.7 degrees, a little more than half a degree. So how far is that? Well, if I go over 0.7, I'm at 69 right here. Oops, need some lead here. I'm at 69 right here. I'm at 69.7 right here. So it would be weird to be warmer than 69.7 for a whole sample of size 25. And of course, if I go this way, I subtract 0.7, I'm at 67, what's that, 0.6? It's all right, 6 and 4. And then 66.9. So it would be weird to be further colder than 66.9 or warmer than 69.7. So what we want to do is actually calculate it and find out the number. So our sample, so we say, what's our p-value? In other words, well, let me write down the hypothesis first. The claim was that it's not equal to 68.3 degrees. Okay, so our null hypothesis is that the mean is 68.3, and the alternative is that the mean is not 68.3. This time we're just checking that it's not 68, which means it could be warmer or it could be colder. In the case of the pit stop times, we wanted to know if it was faster, right? So that's just one-tailed. This is two-tailed. So if I'm too hot or I'm too cold, then I'm going to claim it's not 68.3, right? And I'm going to reject the null hypothesis in favor of the alternative. So we have to test how far over we are. So we find our z value, right? So what's our z value? It's how far over we actually are. Okay, so we are 60. What was our value? 60. Our sample was 67.2. So we were testing, I guess I gotta write that down somewhere. 67.2 is right in here. So we were testing Is 67.2 enough? Oops, sorry. Is it far enough away that that's rare? Well, let's look. It falls somewhere in between 1 and 2 standard deviations. It's a little bit cold, okay? But it's not super weird. Super weird would be like, I don't know, 62 degrees, right? That's way, way over here. That's pretty unlikely. So how far over is this? We would say that our Z is our value, 67.2 minus the mean, right? Divided by the standard deviation, which is the standard deviation divided by the square root of sample size. So we've got, how far over is it? It looks like it's over 67.2 minus 68.3. That's down 1.1 degree. And our spread was 0.7. So we get divided by 0.7. We're down 1.57 standard deviations, right about where I've got the arrow drawn. So is 1.57 really rare? I don't know. Let's find out how much area there is over here. So to do that, we're going to say, we're either going to look at the book, right? Or we're going to use the calculator. I'm going to use the calculator. So how weird would it be? 1E99. I want to be colder. In this case, since I've already normalized the values, I can say I want to be smaller than 1.57 with a mean of 0 and a standard deviation of 1. Oops. Of course, I don't have to put this 0 and 1 in, because when I normal CDF, if it's already standardized, I can just leave it. You could have also not done this step right here, and you could have just said normal CDF minus 1E99, and then just use the actual value, 67.2. But then you have to tell it what the mean is, 68.3, and the standard deviation, which was our, I always like to not round it. So I'm going to put 3.5 divided by square root of 25. So you can either sort of find the Z-score yourself first, or you can just let the calculator do it. It doesn't make any difference either way. And so doing that, we get distribution, normal CDF. We're talking about all the way to the left. Of course, the calculator can't go infinitely far over. So you just go 1 times 10 to the 99th power, which is pretty far. And then it was minus 1.57. What did I do wrong? Oh, minus. Okay. So I get the p-value is equal to 0.058. So what does that mean? That means that there's 5.8% of the area left in here. Whoops, sorry. There's 5.8% of the area right here. Okay, and on our test this time, we were going to test if it's not equal. That means I could miss on this side, or I could miss on this side. Okay, so we're going to double this value. So when we double it, what do we come out with? 2 of those. Is 0.116, or there's about a 10% chance that we would get a sample mean that's this far away. It's like 1.5 standard deviations away. There's like 11% chance. Is that rare? Well, it's kind of rare. It only happens 11% of the time. But we wanted to test, let me check the problem, at the 5% level of significance. So at the 5% level of significance, it's not enough, right? We only got 11%. at the 5%, we'd have to be more rare than that. We would have had to have been colder than that. Okay, so in this case, in fact, even at the 10% significance level, this isn't cold enough. So we would say, okay, it's not far enough over. It's not weird enough. So we're going to say that there's not enough evidence, in this case, to reject the null hypothesis. We're gonna say, well, you know what? I was testing to see if it was 68.3. Okay, the average was to the left a little bit. It was low, but it wasn't so low that it was crazy unusual. So we say there's not enough evidence based on the sample to reject the hypothesis that the temperature is actually 68.3. Had this come out like 0.01, so had this come out 1%, and our value was maybe more like 65 degrees, and it was way over here, then we would say, wow, this average from this sample is so cold that it probably didn't happen by chance, and in which case we would have rejected. So there's not enough evidence in this particular case, and we don't reject the null hypothesis. Okay, so that's twice. Still any questions?
Nothing.
Nothing. Okay, one more faster? And we'll do one more faster. Here we go. Let me see if I can find another one. Okay, here's a nice one. I have to zoom in a little bit again. What I ought to do is just put the book up. I wonder if I can do that. Maybe that's easier. Yeah, we'll just do it this way. You guys, I'll read it. Okay, employees at a construction and mining company claim that the average salary for mechanical engineers is less than that of one of its competitors, which is $88,200. Pretty good deal if you're thinking about becoming a mechanical engineer. Okay, but they're worried. They're worried that it's less, right? Your company's paying less than some other company. That's what they're saying. So they take a look at just one person's, right? Because you just have your own. If yours is, say, $78,000, then that's $10,000 less. You're thinking, wow, this seems like quite a bit less. And so what you'd have to know is, well, how spread out are those salaries? And so you would have to know the spread of the population. In this case, it turns out the population salaries are normally distributed, which they're probably not really in real life, because there's only a few CEOs and they make a lot. And so they were spread out with a standard deviation of $9,500. Let's round it off to about 10,000. So salaries are approximately 90,000 plus or minus 10,000. So if you were $10,000 less than the average, you would say, wow, that feels pretty low, but it wouldn't be that rare because the salaries are spread out with a standard deviation of about 10,000. If you were 3 standard deviations below, in other words, you were 30,000 less, then that would be really low. Only 1% of the salaries would be less than that. So if you were making, if the average is 90 and you were making 60, then that would be really low. Okay, but that would just be using your one salary to test the mean. So what we do instead is take a sample. Now, since the salaries they told us that the salaries were normally distributed, we can take a sample size of a little bit less than 30. And in this case, we take 20. Okay, maybe because there's only so many employees in this company and it's hard to get their salary information. I don't know. But we take a sample of size 20. And so if it's a little bit unusual to be $10,000 less, it would be a lot unusual for a sample of size 20 to be $10,000 less. In fact, the spread of the sampling distribution of sample means is the spread of the population divided by the square root of sample size. So if the population standard deviation was 10 grand, we took a sample, let's make it a little bigger so I can do the numbers. Let's say we took a sample of size 25, then the square root of 25 is 5, and we'd have $10,000 divided by 5, right? Which is $2,000. So it's a little bit weird for one person to be $10,000 low. It would be really weird for a sample of size 20 to be $10,000 low, because the standard deviation of the distribution of all the samples is only 2,000. So if you were 10,000 low, you'd be 5 standard deviations low. So the question is, how weird, right? How weird is 88.2, 88,200, if the company's salary is 85.9? Okay, so that's the question right here. So let me speed through the process. Let's see. So we want to write down the null hypothesis and the alternative hypothesis. So we want to say the null hypothesis is that there's no change. It's not different from what was advertised. So what was advertised was 88,200. And we're worried in this case about the average being less than that. So we only want to test on one side. In other words, we want to know if it's less. So we're going to say that the null hypothesis is that it's 88,200 or more. Which means if we reject the null hypothesis, we're going to find out that the average is less than 88,200. So in the last test, we didn't care if it was too hot or too cold. The thermostat was just busted, right? In this case, if you're making more than the average, great. That's nice, we don't care. We're only going to test if you're on one side. So it's a one-tailed test. So what we're going to do is we're going to look at the distribution of the sample means. Notice I'm drawing the population this time. So this is the sample distribution. Its average, right? Its average is equal to the average of the population, which is 88.2. Its spread, right? Its spread is equal to the spread of the population divided by the square root of sample size. So the spread of our population, looking back, was 9,500 divided by the square root of 20. So we estimated it at about 2,000, just kind of getting our head wrapped around it using a calculator. We got 9,500 divided by square root of the sample size, which was 20. Which is $2,124.26. I'm going to round it off. Sorry about the focus. Okay, so now we're going to say, all right, what are we going to test? We want to test, that's maybe a little too small. There we go. We want to say, okay, we got a sample mean of 85,900 with a sample, right, of size 20. So if this is 88.2, then 85.9 is low, right? 85.9 is going to be low, but how low, right? That's what we want to know. So if the spread is 2,000, then 86 would be one standard deviation. 84 would be 2 standard deviations. This is around 86. It doesn't seem like it's low enough, right? It doesn't seem like it's low enough in this case to be that weird, to be that rare, right? But maybe we will actually calculate it. So where's 85.9? It's right in here somewhere, right? And we'd say, what's the area left over in here? So to do that, we would get, we go write it this way, our p-value is equal to the area that's in this shaded area. So normal CDF, we're going to go to the left, so 1E99. We want to know how weird is 85.9 if the mean is 88.2 and the spread is 21.24. Okay, so in the calculator, here it goes. Distribution CDF minus 1, E99. We wanted 85.9. We've got 88.2, and we've got a spread. I like to type this in without rounding. You could just put the 2124 in, or you can put the 9,500 divided by square root of 20. Since I already did the calculation, I'm just going to put 2124 in. And we get that our p-value turns out to be, what, 139. Okay, or about a 14% chance. So there's a 14% chance that we're in here. So now you go back and you look at what level we wanted to test at. So we wanted to test at the significance level was 5%. And you say, well, the significance level was 5%. We only got 14%. Then this wasn't that weird. We would have had to been way over here, right? It would have had to be much lower than that to be significant at the 5% significance level. So we say this sample, the average of this sample is not weird enough, right? It doesn't provide enough evidence to reject the null hypothesis. So our conclusion is do not reject the null hypothesis. In other words, there's not enough evidence here to show that the salaries are less than what they were advertised to be. And then that's it. Okay, so one more thing. Once you have done 3 in a row, okay, once you've done enough that you can kind of do these steps in your head, you can kind of draw the picture in your head. If you're really in a hurry and you still got a bunch of homework problems to do, then we can just do the whole test on the calculator, okay? But the danger here is you're gonna let the calculator do all the work, so you sort of have to know in your head what work it is that the calculator is actually doing. And so to do that, we're going to go to Stat and go over to Test. Oops, go over to Test. And what we want to do is we want to do a z-test. It's number 1, right at the top. On Thursday, right, we're going to come back, we're going to do t-tests when we don't know the standard deviation of the population. So we'll use number 2 next time. And then Tuesday next week, we'll go down and do a 1 proportion z-test, number 5. And you can see there's more tests on the calculator. And if you want to read about them, there are other sections in the book that we're not going to get to. Okay, but they all pretty much work the same. All right, let's do a z-test. Here's what it says. Do you want to do it from data or do you want to do it from stats? If you do it from data, that means that you have all of the salaries, all 20 of them, and you're going to type them into the list and have it do the calculations. Since they're already done for us, we're going to do it from stats. So mu naught there is the null hypothesis. What is the mean, right, that was projected? So our mean was 88,200. We need to know the standard deviation of the population. So if you don't know that, we have to do the next section and we have to approximate it. But in this case, we do. It was 9,500. What's the mean from our sample? So when we took our sample, we took a sample of size 20. You can put that right down here, 20. And we got an average of 85,900. it was a little bit lower, but if our hand calculation is right, it wasn't low enough. We want to test one of these three tests. It's either equal to, it's either less than, or it's greater than. And in our case, we wanted to test less than, right? So we go down to calculate, we push calculate. It says, "Brr, brr, 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 I'm thinking about this." My z-score turned out to be a negative 1.08. In other words, I'm only a little more than one standard deviation over. That's not too weird. In fact, according to the p-value, it only happens 14% of the time. And notice that that's the same 14% that we just got. Okay, so it did all the calculation for you down to here, and now you have to make a decision. So you got to go look back and look at the problem and say, how confident did I want to be? What level of significance was I shooting for? And you were shooting for 5%, but you only got 14%. So you have to make the conclusion that there's not enough evidence, so we do not reject the null hypothesis based on this sample. There wasn't enough evidence here. And so if you get a little bit faster, you can do a couple of things. On if you're doing one of these, like it's on a test, I would draw the distributions and I would show the work that I showed. I would go through the steps. And then I'd just use my calculator real quick to check. If I were doing, say, 30 of these in a row in the homework, well, I'd probably draw the first few until I realized that the picture's always the same, until I could kind of draw them in my head and have a good idea in my head of what was happening. And then I just use the calculator to quick do the calculation. Okay, so some combination of a little bit by hand, a little bit by calculator, I think is probably the best way to go. If you don't like using the TI-84, then you can do a hypothesis test in Desmos. You can do a hypothesis test, although not the easiest in Desmos. You can certainly do it in StatCrunch and Excel and other programs as well. I just happened to have the calculator handy, so I just did mine on the calculator this time. If you're not sure how to do it on other technology, there's a little bit of help in the book. It shows you some examples on how to do it in some of the other technologies. Okay, so that's hypothesis testing. Essentially, we say, I've got a number in mind. I take a sample to check to see if that number's accurate or not. If the sample turns out to be way far away from what I expected, I reject the null hypothesis. And I say, you know what? I think this is over here because it's different than what was advertised. And then the rest is just kind of crunching through the numbers and getting the actual details. All right, so that's 7.2. That's pretty much it. I'm sorted to the back here, and then there's some problems for you to practice on. I think you guys should go off and practice a little bit, see if this makes sense after you give it a little rest and I'm not here. If you're having some trouble, you can watch the video in the book, right? You could click on Help Me Solve This, and you can always come back during office hours or send me an email, and I'd be happy to help out. Questions before we get going? I think that's probably enough for a Tuesday.
Nope.
Bradley's shaking his head. He's feeling okay. I got a couple of nopes in the chat. All right, well, I'm going to let you go. You guys have a great start to your week. And like I said, if you do have some trouble as you're getting started, please send me a note and I'd be happy to get back and help you. Okay, that's it. See you on Thursday.
All right, thank you.
Thank you.